Hey everybody, this is Charles. I figured there's quite a few people that wanted this explained, and I figured I would just make a, I don't know, 20 to 30-minute video to maybe kind of encapsulate all this stuff and kind of demystify it. And the way I figured is if you guys have a little bit of background on this, maybe you could do some checks out in the field and catch it before it gets to engineering. If you're a CWI, they should have probably went over some of these concepts, but just very briefly and kind of just a basic overview. Also, I'll say I speak pretty slowly, so if you want to, and I also sound like Ray Romano, so I kind of recommend you guys possibly speeding up the video, the playback speed to maybe 1.25 or 1.5. I'll try to be as clear as possible. If there's any questions, feel free to reach out to me. So, a few things I wanted to go over is number one, stresses in pipe, just briefly. Number two, we'll go over stress and strain, that diagram to the left, what you're looking at, and talk about ductile versus brittle. Then the Barlow equation, and how to calculate percent of SMYS, and then safety factors and maybe elevations if I can get to it. It's not too long of a video. So, okay, so let's start off with the stresses in pipe. Overall, there's several. There's the hoop stress, which you guys may have heard of. There's axial stress. There is radial stress. And there is torsional stress. Normally, we are only concerned with radial stresses come into play for thick wall pipes. Torsional stress is a factor, but out of all of these, the hoop stress and the axial stress are of our primary concern. And the axial stress equals approximately half of the hoop stress. So basically, everything gets boiled down to the hoop stress. Now, hoop stress can actually, axial stress is actually aggravated by hoop stress. So as the pipe expands, axial stress is basically longitudinal stress. So in the direction of the pipe body, it can be aggravated by, maybe backfill. So say you have a straight piece of pipe and then you backfill and it kind of bananas it a little bit. So not only when that thing's in operation, you have stress going up and down the body, but now that you backfilled and kind of bananaed it, it means that this on the outer fiber of the body, you've just kind of compounded the problem. If you ever bent anything, you can kind of tell that on the outside of it, it's in tension, and then on the inside here that I just marked is in compression. So although axial stress is certainly a problem, it can be aggravated by either mishandling the pipe out in the field, in combination when it's in operation, if you guys backfill it or maybe banana that thing, so it makes it even worse. Okay, so the second thing I think I want to talk about here is ductile versus brittle, which is what I have notated right here. So a ductile material essentially means something pliable or stretchable or elastic. You don't think of metal as being elastic, but they actually are. The reason why we want ductile materials, ductile materials are pliable, and before they fail, they actually can give you some signs of failure. So it gives you an opportunity to actually identify it before, catastrophic event. I'll get to that in a minute. Brittle materials are things that are not pliable. And in that instance, they just break suddenly, and there's no signs. They just kind of give out. And then it's made worse by temperature as well. So materials that are cold become more brittle. And that seems kind of counterintuitive, or intuitive. And then materials that kind of get heated up a little bit become more pliable, and that kind of is intuitive. We would think anything that you would heat up would be able to be more malleable. So those are kind of some additional factors. Now, a way they traditionally kind of illustrate this point, and maybe some of the welding inspectors watching this, like I said before, they kind of go over the stress strain diagram, and I'll get to that briefly. But the way they basically determine if a material is ductile or brittle is they will get a sample that's being shown below here, a tensile sample, and maybe they mill it down in the center here and they round the edges, and then they're threaded on each end, and they'll put this thing in a vise on either end, and they will apply a load and pull this thing apart. And before they do that, they will actually put two little dots here, gauge marks. They'll pull on this, they'll wait till it breaks, and then they'll come back and they will measure the distance away, the final distance away before it broke. And then they can basically calculate this, the general equation. It's not very complicated, just length final minus length initial all over to length initial, and then times 100, and that'll actually give you your final percentage. Overall, anything 5% elongation is what they'll say, elongation or greater is considered ductile. You could probably look right on the MTR. The MTR will more often than not have the percent elongation. So as long as it has a minimum of 5% elongation, all the way I've seen elongation all up into the 40% range, which is an extremely ductile material. Also on the MTRs, it goes over yield strength and ultimate tensile strength, but I'll explain that. But overall, that's how they essentially know if a material is ductile or not. And like I said before, as engineers, you want to use a ductile material. So it gives you a little bit of a notice before it fails. Now, while they pull on this thing, right before it fails, and I'll get to this in a second, it kind of necks down is actually the technical name. Also necking down. So this will actually thin out before it breaks, which is kind of intuitive. But anyways, so necking down is another concept we should keep in mind here. Necking. Okay, so let's go over to our stress strain diagram. Essentially on the y-axis you have stress, that's signified by sigma, and it's in units of psi, or it's another way of just saying pounds per inches squared. Stress over a specific area. And then on the x-axis you have epsilon, which is inches over inch, which is essentially dimensionless. And all this is saying is for the amount of stress that we put onto it, we're going to get a certain amount of stretch or elongation to it, or strain. So basically, everything an engineer deals with or designs to is up to this point A. And essentially, anything in this zone is considered the safe zone, and everything that we design is in that area. They'll find out the maximum stress, and then they'll usually cut it in half with a safety factor. So what is this safe zone that I'm referring to here? This is essentially everything from point 0 all the way up to here is what they call, to point A is the proportion limit. Well, what does that mean? It means for every unit of stress, PSI, there's an equal unit of strain. So it's a 1-to-1 relationship. So the slope, essentially, rise over run, is 1-to-1. Anything that's in this area or falls in this area is considered, it obeys Hooke's law. I don't know if anybody's ever heard of that. So as long as you're in this area here, this area, we'll say, abides by Hooke's law. Well, what's Hooke's law? Well, Hooke's law says it's basically the behavior of spring, and that's usually represented by F equals negative kx. This is the force, this is the spring constant, and essentially how stiff the material is, and this is the displacement, or how much you've stretched something. So overall, the main takeaway is anything in here, the materials will act as a spring. If I pull on something, like let's just say like a spring, and I pull on it and I don't pass point A or B, and I let go, that material will go right back to the way it was. That's what we want. Now, so essentially, point A is the limit where it's proportion, and then from A to B, this is called let's just say this is the proportion limit. And then from A to B, it's no longer a one-to-one relationship. As you can see, it's curved here. That slope is kind of thrown off a bit. So this area right in here from A to B is actually called the elastic limit. So from point A to point B is the elastic limit. It means if you reach point B and you let go, it'll go back down to zero and act as a, when you take the stress off, it'll go back to its original shape. The whole problematic area, what I want to really talk about here is, and like I said, the CWI talks about this, is from this area from like B to C is actually what we call the yield point. Okay, what does that mean? So back to this necking concept. That's basically when deformation starts. And after you hit that point, the material will be permanently deformed. Obviously, that's a bad thing. Again, we want to design everything in this zone. We want materials to behave as a spring. So yield point might sound a little bit familiar if you remember, SMYS, specified minimum yield strength. All of our piping and fittings has a specified minimum yield strength. So X52 is 52,000 psi. You got your X60, that's 60,000 psi, and so on and so forth. X70, grade B, throws a lot of people off. Grade B is actually 35,000. That's the weakest typical material we deal with. So that's essentially the yield point. So the last point on our chart that I want to talk about is called the ultimate tensile strength. And I should note that this chart right here, this stress strain diagram, there's a lot of things you can derive from this. I'm not going to get into all of it. In fact, if you're a civil engineer, a mechanical engineer, probably well over a third of your semester is just focusing on this graph or this chart and everything you can derive from it. You can derive the stiffness of material, how tough a material is, a lot of different equations you can derive from here. But like I said, I just want to give you a general overview of this because it's important before I introduce the Barlow equation. And again, it would be good to probably take a look at an MTR and look at the heat number somewhere on that MTR. They're going to tell you the yield strength. They actually test all the materials that come out of a mill, any batch of steel. Out of one batch of steel, they'll make a variety of things. They'll make pipe, they'll make plate, they'll make elbows, they'll make T's. They make a whole lot of different things from one batch of steel. And what they do is they'll take a sample out of that steel and then they'll actually do mechanical testing on it. Like this test I was just referring to here, a tensile test is what this is called. And then after it breaks, they'll record all of that information and they'll actually denote it on the MTR. So you'll see a column for yield strength. Say we have X42 piping, the test results should break over 42,000 psi on the MTR. So it's not going to break right at 42,000. You'll see on the MTR, it'll say, okay, X42 piping. It'll say probably 52 or 53,000 psi's when it broke, but it met the requirements of the minimum of 42,000, and so on and so forth. For X60, 60,000 psi, it's not going to break right at 60,000. It's going to break over like 65, 66, 68. It'll vary for per material. Last thing I want to notice note before I move on here is that this chart, this is kind of a graphical representation, not every steel behaves like this. Some graphs, some stress strain diagrams will look a little different. It's not always obvious where the yield point is or where it starts to deform. So, I mean, you might have something like this for a material. Let's see, sigma and epsilon. And what they'll do is if it's not obvious where the yield point is they'll come out here at 0.02%. And they'll actually strike a line. They'll draw a line diagonal, and wherever this intersects on that curve, they'll be able to actually pin down approximately where that yield point is. Maybe you've heard of pressure versus volume charts for pressure testing. Sometimes they have to test pretty near 110% SMYS, or maybe a little bit more. And what they're trying to figure out during that PV plot is, we already know 1-to-1 relationship, we're in a proportion limit, but once we get up past A and up to B, that's no longer a 1-to-1. And as long as that offset method, is before that point B, then we're pretty much in the safe zone and can assume that we haven't permanently deformed or damaged the pipe. Okay, so let's talk about the Barlow equation. I had to give you a little bit of background. So the Barlow equation, and maybe you've seen this before, it's 2 times S times T all over D. And then there's a couple other factors out here, but I'm going to erase these, but I do want to make sure that they are here, and we'll talk about them when we get the safety factors. So this portion here, I would say, is the physics of piping and, essentially stress, pipe stress. And then this part here is Code of Federal Regulations, Title 49. 192 is what governs most of our, pretty much everything we do out in the field: the construction, installation, material selection, design of piping, cathodic protection, welding. I mean, it goes through the whole thing. But let's just put that out of our heads here for a second, or the time being. I'll erase this, and let's just focus on what this equation is. So let me go over the basics here. D is the diameter, and that's the outside diameter. Now, I need to note here that it's the actual outside diameter, not just the nominal. So 12-inch nominal piping isn't just 12 inches on the outside diameter. It's actually 12 3/4. Essentially from 1 inch all the way up to, 12, or I don't even know if they make 13-inch piping, but up until you hit 14, the outside diameter is not actually, 2-inch piping is not 2 inches in outside diameter. 12-inch piping is 12 3/4. When you hit 14-inch, then it's a 1-for-1. So 14-inch piping, the outside diameter is actually 14. 16 inches is, OD is actually 16 outside diameter. The reason I say that is because if you don't put in the right numbers here, you're not going to get the right, you're not going to get the right answer, and it's going to skew something. So let's just make sure we keep that in mind. 2 is just a constant. It's like, this equation is half of a pipe, half of a shell. The 2 is 2 sides, so you basically have a full cylinder. The S here is SMYS, or specified minimum yield strength. That's your X42, X52, etc. And then your T here is your material thickness. What I normally tell people is put 100% here as a subscript to this P, and this is P for pressure. Well, what's that 100% mean? Well, let's give a quick example what that 100% is. So let's say we have 12-inch piping. It's X52, and it's standard wall, and standard wall is 0.375. If we put this into this equation, I'll just do it longhand here. P 100% equals 2 times 52,000 times 0.375, and that's all over 12.750. If you run that through your calculator, you should come up with P equals 3058 psi. Yeah, okay, so what does that actually mean? So what that means is your for 12-inch pipe, we're just talking about 12-inch pipe here for right now. That means 3058 psi is at this point, roughly, at your point A. That means the 100% value. If you go over that, it's your yield point. So just keep that in mind. So 3058 is this equation will give you the 100% value of when we're kind of encroaching on the danger zone of what that material can withstand. After that point, we're getting into yielding territory where we permanently deform the piping. And just by inspection, I just want to take a step back here. If we actually look at this equation, this denominator, the bigger this denominator is, then the smaller this pressure or rating would be. And the larger these factors are in a numerator, then the higher this value goes. So it's safe to say, you know, if you have 36-inch piping, more than likely it's going to cut down what this is good for. Well, why is that? Why is that relationship like that? If you think of the equation real quick, F equals P times A, essentially the force exerted on an object such as piping, the larger the surface area is, then the higher the force is going to be. So that's why smaller piping like 1 inch or 2 inch is never really a concern. That's why it's a grade B 2 inch, because that piping is so small. This denominator is so small. It has has little to no effect on how much the 100% rating is here, if that makes any sense. So larger, let me go back here. The larger A is, then the greater the force. So that's why larger piping has more internal surface area for the hoop stress to act against, and that's the reason why. So if you just play around with this equation with just pump in a few factors on larger diameter, put in 36-inch piping, X60, and then put in 2-inch piping, the worst grade, which would be grade B, 35,000, and you'll see the difference of how much higher 2-inch is going to be for the 100% value than it is on 36-inch. Okay, so the last thing on the Barlow equation that I wanted to kind of go over is if this equation here tells us what the 100% value is, the whole, then we should be able to find a part of that whole. And that's the same way of just saying, let's find a percentage of it. So percentage of SMYS. If 3058 is 100% of SMYS, then you should be able to figure out any pressure that you put on piping. You should be able to find the percentage that you're stressing the piping. So what do I mean by that? So let's here's a for instance. A lot of you guys are pretty accustomed to seeing a test pressure of 2160. I'll get to the reason why it's 2160. But let's just say 2160s typically are minimum test pressure on a lot of fabrication sections. And if we know what we're pressurizing it to, and we know the 100% value of 3058 PSIG, then this should come out to be about 70%. Same thing at 2220, our maximum test pressure, we should be able to find out what percent of SMYS you're at. There should be what, like 72? Let me double check. Yeah, it's about 72.5%. Now, you'll see in some specifications, like welding specifications, will say, hey, this welding, you're allowed to have a girth weld this close to a threadlet weld as long as it's less than 20% SMYS. So right there, as long as you know the 100% value of any piping you're looking at, you would just take your part of the whole. Okay, so how would we figure that out? Well, most of the piping, new piping that we put in, we always design for the highest 1440 is typically what we do. 1440 is pretty much the max that a class 600 flange system can withstand. So we pressure test all of our pipe and design it for 1440. That's not always the case, but I'm just saying new installations, more often than not, we're going to shoot for maximum design of 1440. So it doesn't have to be that. But let's just say we're welding on 12-inch pipe. We need to move, I don't know, the weldalet. Instead of being 4 inches away, the welding spec says you can move this to 3 inches as long as the pipe in operation is less than 20% SMYS. So all we would need to do, we would take 1440. This is the more conservative approach, I should say. This might not be the operating pressure, but this is the max it'll ever see, and then we'll just divide it by our 100% value, and let's see what that comes out to be. Okay, that comes out to be 47%. So that's well over 20% SMYS, so we wouldn't be able to actually move that weldalet any closer. You can do that for anything. So maybe you just want to know what stress is on that pipe when it's actually in operation. And you could probably talk to one of the operating personnel and say, hey, what's this pipe actually run at? Or we could look through our system and see what the average operating pressure. Let's just say they operate at typically 1100 PSI, which is pretty common for down south in a lot of the systems there. and then just divide it by 3058. And what does that come out? That comes out to be about 36%. So it's still over 20% SMYS. But basically, that's all you have to do is essentially to establish what percent that you're actually stressing that piping at. So 1440 divided by 3058, 47% would be a little bit less than halfway here, right? This is about 47%, and that's at 1440. Actually, I should probably put that out here. 1440 psi is 47% of the 100% value. Again, you can do that with any pipe. Like I said, I wanted to reiterate this so that nothing gets misconstrued. This is just for 12-inch pipe. I should write that up here. This is for 12-inch X52 0.375 wall only. So this graph the concept is the same. Obviously, this 3058 isn't 100% or the top value of 10-inch pipe. 10-inch pipe's gonna be completely different, but the concept's the same. And as soon as you you pump in the numbers into here, whether it's 10-inch, then obviously this 3058 is not going to be the same. That's only for 12-inch X52 375 wall. If I change any of that, whether it's the diameter, the grade, or the wall thickness, it's going to change completely. So I just wanted to stress that before I moved on. Okay, so now one of the last things about this Barlow equation I need to go over is, remember earlier I said there's a few other factors here. There's F times E times T, and this is what we were talking about before that we called safety factors, or additional factors, and it's by Code of Federal Regulations, Title 49, CFR 192. Okay, well, the first one is literally the safety factor. The E stands for longitudinal joint factor, and then temperature stands for the temperature. As long as we're at 250 degrees and below, then this just turns into a 1, which is 99% of the time. Most of our piping is designed for a temperature 250 degrees in operation or below. This E is 99% of the time is going to drop out and become a 1 because newer age piping, high frequency welded seamed piping, is a lot better than it used to be years ago. However, if it's spiral wound piping, if it's furnace butt welded piping, or something of that nature, then this might come into play. But more often than not, seamless piping, ERW piping, double submerged arc welded piping, this is all 1. These just basically, they drop out. Anything times 1 is just itself. So that's why these become non-factors. Okay, so what's this F then? Well, this is, like I said before, it's a safety factor. Well, how do they determine safety factors? Well, what they do is they'll actually make a study, and they'll try to determine what areas are of high consequence, or HCA. You might hear that coined in the future, high consequence areas. So what they'll do is they'll actually take a pipeline route. Let's just say this is 1 mile or 2. Let's say it's 2 miles of piping. For every 1 unit, which is 1 mile, they'll go off the center of this pipeline 220 yards each way, and they'll actually count up how many homes are in that 1 mile area. Not just homes, but recreational areas, theaters, if there's anything, any kind of outdoor where there's big public gathering. Is it 2-story buildings, 3-story buildings? So generally speaking, and what you can do is you can actually go to Code of Federal Regulations here, and it actually goes through these definitions and what, like I was just talking about here. Here's your longitudinal joint factor. Here's your seam value. If you have furnace butt welded, you have to put 0.60 in there. Here's our temperature values. So 250 degrees or less, we're good. It's a 1. If we're over that, then the material properties of steel start to degrade, and then you have to put in 0.96, so on and so forth, and then class locations. So if you guys ever have a chance, 192.105, which is right here, is a good section just to review to get a little bit more background on it. And like I said, this is law. Code of Federal Regulations is actually law. It's you shall do this. But this is a good background just to take a look at it if you want a little bit deeper, context to what we're going over. So back to the class locations. So essentially, a class 1 area is a location with fewer than 10 homes within a 1 mile stretch, 220 yards off a center. I do believe if it's greater than 10 homes but less than 46, then you're in a class 2 location. And if it's greater than 46 buildings, or if it's a compressor station or a meter station, it's automatically a class 3 by design. Well, what is that? So let me write these down. Class 1, like we said, is up to 10 homes, 1 to 10 homes, and that class 1 factor is actually 0.72. A class 2 is 10 but less than 46 homes, that is 0.60. And then a class 3 is 46 homes or greater, or if it's a compressor station, meter station, if there's an outdoor park or a recreational area or a theater or something like that, then it's an automatic class 3. Now there is a class 4 location, and that gets you'll probably never see that in your lifetime. It's for highly densely populated areas and multi-story buildings. That would be 0.40. But overall, these 3 class locations everybody's pretty much familiar with. You can see them sometimes on the alignment sheets. Okay, so what does that mean then? Okay, so class locations. Basically, a class location and these safety factors is almost like it's like a speed limit, right? So if you're out in a rural area and you're driving down a highway, the speed limit's 70 miles an hour, right? And then once you get in a little bit more of a populated area, it starts to go down. So maybe it's sparsely, peppered with some homes. Then it drops down to 55. And then once you get in like near the downtown or the more densely populated town area, then it's down to 25 miles an hour. So just think of that as your rural, your 70 miles an hour is your 0.72. Your 55 miles an hour is your class 2. And then your class 3 is your 25 miles an hour. That's a good way to think about it. So, okay, so what does that actually mean, though? It means your 100% value that you just determined over here, it means you have to cut that by whatever factor that we've established the area is. So if this 12-inch piping, and we found out a 100% value is 3058, what Code of Federal Regulations says, no, you can't run that at 100% of its strength right before the yield point. That's crazy. So what you have to do is you got to take this, and then you multiply it. Let's just say it's class 3 area. We're in a compressor station. So now we got to take half of this, or 50% of it, and what's that come out to be now? Well, that comes out to the maximum that you're allowed to run that piping there is 1529 psi maximum. Okay, so where is that over on our stress strain diagram? Well, it's dead center right here of our in our safe zone. So right now this is class 3, and that is 1529 psi G. Okay, what would be our class 1? What was the maximum pressure we can run in a class 1 location, assuming it's a rural area? That comes out to be about 2201. So 72% is probably somewhere up in this region, and that would be our class 1, and that is 2202 psig. And in our class 2, same thing. We just take our 100% value. We take 3058, and then we multiply that by class 2, 0.60, or 60% of that. That comes out to be 1835. So 1835, this is your class 2, 1835. So that would make sense that if you're in a high consequence area where there's an increased risk of loss of life or property, then they're gonna limit you on what you can stress that pipe to be. So any piping in a compressor station, I don't care what diameter it is, any piping in there cannot run higher than 50% of its SMYS, and that is a safety precaution. Any piping, so that's why you'll see out on a pipeline, you'll see one location will have, let's just say it's 36-inch piping and it's X70 piping, right? You'll see probably 3 different wall thicknesses depending on your class 1 area, class 2, and your class 3. And that's where this all comes from. In a class 1 area, 36-inch piping should probably be like 515 wall. Class 3 should be 0.741. Well, how did I figure out what my wall thickness needs to be? Well, I can just rearrange my equation. It's the same premise. I wanted to go over that real quick. So let's get rid of all this. And all I need to do, I'll put this back here. We'll just say FET times E times T. And all we need to do is rearrange our equation here. So we would take this over here. We would rearrange this with a little bit of algebra. We can isolate T equals, let's see, PD. And then we would have to divide by 2SFET. And that's how you would figure out your minimum wall thickness, your design thickness that you would need to procure depending on the class location. So let's run a hypothetical here. Let's just say we have 36-inch piping. Let's just say it's X70 and it is in a class, let's just say it's a class 3 area. So we established that as 0.50. Well, if you want to pause this, you could figure that out and see what the minimum thickness that you need to have your piping for in a class 3 location. What's that come out to be? Okay, so let's run through it. So as we said before, our design temperature is less than 250, or we have double submerged arc welded piping. So this drops out altogether. So we would just plug in everything we need here. We would put in, we want a 14, I'm sorry, I didn't give you the, let's just say 1440 like we always design everything to practically, times the diameter, 36 inches, and 2 is just a constant, and then we would multiply that by the SMYS, and multiply that by 0.50. And this is PSI as well. So just by canceling units here and here, that'll drop out. You should come up with a thickness by design at 0.741 inches. So you're left with inches here. Well, I've been on one project one time that they actually procured and had the piping manufactured literally to that wall thickness. But more often than not, if you know this is going to be your minimum, you would probably say, well, three-quarter wall is pretty standard. That's a pretty standard off-the-shelf kind of wall thickness. So you would procure at least 750 wall, 36-inch piping, X70, and that's the minimum thickness you would be required. Okay, and finally, and I don't think I'm going to have time to go over elevations here. It's becoming a long video, but I did want to go over one last thing here. Okay, so for pressure testing, how do we know what the minimum test pressure needs to be? Now, more often than not, depending on what company you're with or depending on the project, more often than not, but not always, we test everything to the highest level and we design everything to the highest design criteria we can. So the highest design criteria is typically 1440 PSI. Over that, you would have to actually increase the 900-pound flanges. So any kind of class 600 system, 1440 is like our upper ceiling of what we typically go for. And why is that? Well, class 600 ANSI class 600 flange is good for 1480. So, okay, well, what do we have to pressure test to? But again, it ties into these safety factors, and it's the same thing. Code of Federal Regulations. You can go down through here, but they're going to tell you eventually. They're going to say, okay, for your class 1 location, the minimum you have to, and we're going to say 1440 design, right? More often than not. Like I said, not all the time. It could be your MAOP or design, or the designs of the system that you're tying into could be, I don't know, 900 pounds for the max. Then you might not have to go this high. Well, let's just treat this as it's a brand new project, or we're in a class 3 location. Let's just say we're putting this into a compressor station. It's automatic class 3, and the whole station's being designed to the highest pressure we can for a class 600 system. What they say, well, I'm sorry, let's do class 3 here real quick. Class 3, they're going to say, okay, your safety factor is the highest here. You're going to have to, but for a class 3 location, your multiplication factor has to be 1.5. And just think of this as 150%, right? So you have to take whatever pressure you're trying to substantiate, you have to multiply that by a factor of 1.5. And what does that come out to be? If you multiply 1440 by 150% or 1.50, the minimum comes out to be 2160 psi G. And that's why you'll see that as a minimum a lot more often than not. You'll come up with that. For class 2, then you could take your 1440, and then you're going to have to multiply that. If you look in Code of Federal Regulations, they say for class 2 location, you're going to have to multiply by 1.25 or 125% for 8 hours or 4 hours or whatever it may be. Well, that comes out to be 1800 psi G. For 4 hours or 8 hours. Now, the class 1 criteria is actually gone away. Years ago, I think prior to 2020, you were allowed for class 1 location, you were actually allowed to run a test at 1.1 or 110%, but they've gotten rid of that. So this is no longer even a factor. Basic rule of thumb with this is whatever class location you're in and Code of Federal Regulations, you have to test to the next higher class location. So if we're in a class 1 area, then you have to test a minimum to a class 2 criteria. If you're in a class 2 area, you have to test 1 higher than that typically. And basically that's where this comes out to be. And this is either for 4 hours, if we have a short fabrication section, and this is just changed for us internally to anything less than 170 foot of piping or fabrication assemblies, then we can get away with a 4-hour test. If it's greater than 170 foot, then we have to test for 8 hours for a minimum of 2160 and typically a maximum of 2220. And the reason being is your flanges are your limiting factor. How they get that 2220, 1.5 times 1480, which is the class 600 flanges, that equals 2220. 2220 for some companies. Other companies actually allow you to go to 2245. And where that comes from is ASME B16.5. It actually tells you you're allowed to go 1.5 times your 1480. And then you can round up. You're allowed to round up to the next highest bar, if that's metric, or the next 25 psi increment. So plus 25, that gets you 2245. But a lot of companies do the 2220 criteria and call it a day. So as you can see, the multiplication factors for your test pressures are based on class location. More often than not, most of the designs are going to be to the max of everything. Why is that? Well, the reason being is if you're in a class 1 area and you put a pipeline in, and then 10 years down the road there's a bunch of new homes that get built around your pipeline within that 220 yards. Now you have to reclassify the pipeline, and you have to either have to retest, or you're going to have to increase the wall thickness or increase the grade or something to make sure that that cushion or that safety factor is abided by. If you're in a class 1 area and it goes to class 2 and you don't have the piping, the pipe wall or pipe grade high enough to make sure it's running below 72% of its SMYS, then you're gonna have to make some changes. I would get into elevations. I think it's running a little bit too long here, but if you guys, maybe I'll make a separate video if you guys really want me to explain how elevation has an effect on static head pressure and how it adds stress to the piping at the low points and how you lose pressure as you go up. I can certainly make that video, but I was not anticipating a 45-minute long video. I hope you guys enjoyed this. If you have any questions, feel free to reach out. Appreciate it.